All right, guys. So welcome to the workshop on RNNs, which stands for recurrent neural networks. So, oops. So the agenda for today, first of all, we're gonna be talking about what RNNs are, and then we're gonna go over some like examples of how they're used. We're gonna go over vanilla RNNs, which is kind of like it's an example of a model that basically no one uses anymore, but it's a really good kind of intro for learning how RNNs work. And then after that, we'll go into more complicated RNNs like LSTMs. Um, and we'll look at like deep RNNs, so like how do you stack RNN cells and learn more complex models. And then finally, we'll look at a specific kind of type of RNN or type of use case of RNNs called seek-to-seek, and that's also what the notebook is going to be based on. Yeah, so first of all, what are RNNs? So basically, your traditional neural network can only do that what you see on like the picture on the left-hand side, which is one-to-one. So it takes a fixed length sequence and produces a fixed length sequence as output. So the reason that this might not work in a lot of situations is like if your input changes length. So for example, if you're processing like something over time, like a video or something, if you want to process a bunch of video frames, then you'll have to feed all those video frames in as a fixed length input. But if you want to process a new video that has like a different length, so maybe your first one had 5 frames, your next one has 6 frames, then you'll need a whole new network to process that new one. So that's not good. So the way we solve this is by using RNNs. So basically, these are neural networks that are designed to process series of inputs and outputs instead of just singular inputs and outputs. So the basic idea behind them is that they, like each RNN cell, kind of remembers information from previous inputs, and it uses that in order to process new inputs and produce its output. So yeah, like I said, the benefit of it is that you can take an arbitrary length input and produce an arbitrary length output. And there's a lot of different use cases, or there's a lot of different like categories of use cases. The first one is you can obviously use it just like a traditional network, just to do one-to-one mapping. You can also do one-to-many, and then many inputs to one output, or many inputs to many inputs. And there's a couple ways you can do that last one. So some specific examples of how like each one of these categories is used. So if you want to do one-to-many, that could be like music or story generation. So imagine like you're given some kind of genre like classical music, or I don't know, like a comedy story or something. And then your network generates an entire series of outputs, which is like the entire story or um, the entire piece of music. So that would be one-to-many. You can also do something called like sentiment classification, which is basically where you take like some text or some like thing that has variable length. So it could be like, I don't know, like YouTube comments or movie reviews or something, and then you produce like whether it's positive or negative, or like the emotion that the person who wrote it tried to express. Or like stock market prediction. So you take a series of stock market trends, and then you predict whether the next one's going to go up or down. That would be many to one. Language translation is many to many, generally type 1. So you can think of like feeding in a sentence in one language and then producing a sentence in another language, but the two sentences might have different lengths, right? So you can't just have a direct like one-to-one mapping of each word. So that's where that many to many comes in. And then if you want like many to many part 2, then examples of that would be like name entity recognition, which is basically where like you take a body of text, and then for each word you say like what kind of word it is. So if it's like a proper noun, like a location, I don't know, an object, stuff like that, or even like next word prediction. So think like on your phone, like when you're typing, you know how it predicts the next word. That would be like many to many type 2, because it takes like the entire series of inputs that you took in before, but at every time step it only produces one output. So yeah, those are just a few examples of how we can use RNNs to solve different problems. So one side note, I'm going to talk about vectorizing words for a bit, because a lot of RNN usage is often in NLP. So it's important to know like how the inputs are processed before they're passed into the RNN. So I talked about this in the, I think, feature engineering workshop. So the first kind of basic way that we encode words is one-hot encoding. And this method often works well for a variety of use cases. And it's the upside to it is that it's very, very simple and very easy to implement. So the idea behind this, I'm just going to go over it very briefly, is that you assign an index to each word, and your your word vector is going to be equal to the size of your dictionary, and then it has a 1 at the index of the corresponding word and 0 everywhere else. Second way to encode kind of sequences of words is a thing called bag of words. So like think like if you had a document and then you wanted to encode one sentence at a time, then each sentence would be encoded with a count, kind of like a sum of the one hots of all of the individual words. You can even encode like a whole passage with bag of words. So the upside to this again is that it's very simple, but obviously it loses a lot of information, like how the words are ordered, and that can, make it perform worse. Although in general, it's very often used as kind of a baseline for NLP models, and it actually works pretty decently in practice. So the third kind of major way that you vectorize words is word embeddings. So these are usually things that are learned by a neural network. For example, like glove and word2vec, those are like word embeddings that people have used for a while. I don't think, or they are a neural network, I think. At least word2vec is like something like a 2-layer neural network. Very simple, but it like generally works pretty well. And yeah, the another kind of category is learned vector representations that you train with text data. So generally these are trained by like scraping Wikipedia for all of their text data and then learning like how to represent kind of the English language in a convenient way. So like modern examples of this would be like Elmo and BERT, which I think Google came up with. And BERT is just like a massive like neural network that lets you encode words into a very a vector that is like very easy to then process and do future tasks on. And yeah, the upside to these is that the vectors are context dependent. So if you were to encode like sentences or words using these vectors, then the resulting vector would kind of already know the context. So it would interpret that. So the vector would interpret that word in the context of where it was found, which is really cool. So at this point, if anyone has any questions, you can just unmute yourself or ask in chat if you want. All right, so I'll move on for now. So now I'm going to start talking about vanilla RNNs. So what a vanilla RNN looks like is basically what you see on that bottom right side. So there's going to be what we call an RNN cell, and then it takes an input and a hidden state. So the idea, and then it produces also a hidden state. So the idea behind the hidden state is that it's supposed to represent like all the information that you've seen before into just one vector. And yeah, so basically you're incorporating the RNN cell learns to incorporate all the info from the previous input. So theoretically, you should be able to remember everything that you've seen before just with that like fixed length hidden state vector. So when RNNs process inputs, you can think of it as processing inputs according to like different time steps. So for example, if you were processing a sentence, like Go Bears or something, the first input might be like some kind of start token. So that would be the input at time step 0. And then the input at time step 1 would be Go. And then time step 2 would be Bears. So after you process each time step, the RNN cell produces some kind of hidden state, and then that hidden state is passed into the next time step for the next RNN cell to then combine with the next output. And specifically for vanilla RNNs, this is the activation function, or the function that allows the RNN cell to produce the hidden state and input. So we have two weight vectors. One is the weight vector associated with the hidden state, and one is the weights associated with the input. So you multiply the weight vectors by, or you multiply the hidden weight vector by the hidden state, and then the input weight vector by the input. You add those together, so you have to make sure that the dimensions match, and then you apply a tanh activation function on that, and that's what you use as your next hidden state. And so if you want to obtain output from this, oftentimes you can't just use the hidden state directly as output, because sometimes you want the hidden state to kind of encode more information than what your output needs. So the way people generally obtain output is they take the hidden state, for example, the hidden state produced from time step k, and then at time step k, they produce as output a linear transformation or a nonlinear transformation of that hidden state. So that could just be a simple like weight matrix multiplying the hidden state and then transforming it using some kind of activation function. And then if you had like the diagrams we've seen before, if you had like a one-to-many or like many-to-one, or I don't know, a different type of architecture, then you would only be obtaining outputs from some hidden states, and you would just kind of throw out the rest of them after you're done with them. And yeah, this is like when you want to like transform the hidden state into output varies on a case-by-case basis. So at this point, does anyone have any questions? All right, so I'll move on. So one important concept about like RNNs in general is parameter sharing. So the important thing to know is that basically in this diagram, there's only like one singular cell doing all the work. So it's not like each time step has a different cell. Each time step has the same cell, and then the weights are shared between time steps. So so each layer only has one cell, and then the weights for that cell are reused in every time step. And the benefit of this is that if you were processing like an arbitrary length input, then obviously you can't have a different cell for each time step, because if your input changes, then you would have to learn a completely new set of weights for that like the next length. So like if you are used to only processing 5 length inputs and you suddenly get a 6 length input, then you won't have a corresponding set of weights for that 6th length or that 6th input. Because we do parameter sharing, you don't have that problem. So it can kind of process these things infinitely. And the idea behind like why this works is that basically you're assuming that there's some kind of fundamental relationship between how the inputs produce outputs, and that relationship doesn't change. So given the hidden state, the hidden state and the input, you can basically determine in the same way at every time step what the output should be. So if you look at this diagram, this is like the left side is the singular RNN cell. And then it's passing on like the V vector, which is the hidden state vector, to itself. And then when you kind of unfold it, you can see that same cell being used at different time steps. Anyone have any questions on parameter sharing? All right. So here we have just an example of kind of how vanilla RNNs process data. So assume that our task right now is to predict the next letter that we want to type. So our input would be a sequence of letters, and then each time step would consist of one letter. So you can imagine that this is probably a many-to-many type 1. So if we go back a bunch of slides, yeah, many-to-many type 1, or sorry, many-to-many type 2, because at each time step you have to produce a letter for the next, for the prediction. And how this is going to work is Um, yeah, so the input is a sequence of letters, and then the output is going to be your sequence of predictions, right? And then the plus side to RNNs is, as you can see here, it can kind of be applied recursively. So before, like if you were to feed in one input at each time step and then produce one output at each time step, then that would be like a many-to-many type 2. But if you want to apply it recursively, then it can even be turned into a many-to-many type 1, or like combination between type 1 and type 2. Because the idea behind this is that you just pass in a G, and then you predict that the next letter is O, and then you pass in your prediction for the next time step as input, and then you can basically predict the entire word, even if you're only given like 1 or 2 letters. And that's assuming that your RNN can do really well. But basically, this is also the idea behind sequence-to-sequence networks. And it just illustrates that RNNs are really powerful and like they're versatile in how you want to use them. So now we're going to go into some of the problems of RNNs. So before we start, does anyone have any guesses on like what a problem of RNNs might be? Okay, so I'll just go into it. So basically, the vanilla RNN is bad at learning long-term dependencies. So if you had like a really, really long series of input, and then you kind of have a dependency between time step like 1,000,000 and time step like 5, then using a vanilla RNN, it's generally been found that it can't really deal with cases like that. So it basically forgets what happened at previous time steps. And that's because of the vanishing gradient error, or the vanishing gradient problem. So there's kind of two sides to this. So first there's the vanishing gradient, and then there's the exploding gradient, which are kind of two sides of like the same problem. But obviously the exploding gradient can be fixed a lot easier if you just like limit the gradient to a certain range. So like if you clip the gradient between like 0 and 1, or like apply some kind of like sigmoid function on the gradient or something, that solves the exploding gradient problem. But the vanishing gradient is a lot harder to solve. So the idea behind vanishing gradient is that when you're back propagating the error, in order to update your weight matrices, the like gradient kind of gets shrunk through each time step. So if you, for example, if you were back propagating the error at time step k, then obviously you want to calculate the derivative of the error at time step k with respect to the weight matrix, right? And but you can kind of consider the error at time step k as dependent on every single previous hidden state vector, because like the hidden state at time step k minus 1 produces the hidden state at time step k, and then the hidden state at time step k minus 2 produces the hidden state at time step k minus 1, which then produces time step k. So the total kind of gradient or derivative with respect to the weights is equal to the sum over all previous time steps of this quantity right here. So it's the sum over all previous time steps of how the error depends on the weight through the hidden state at that time step. And that was kind of a complicated explanation, so I can explain again later if you guys have any questions. But for now, let's just look at this term inside the sum. So the DEK, DHI times DHI DW. So what that means is like that term is basically telling you the contribution that the weight matrix has on the error through the hidden state at time step I. So for example, like if you want DEDW at time step like 5, then one of these might be at time step 3. How does that hidden state factor into that entire gradient? So if we expand out this, like the inside of the sum using chain rule, then we end up getting derivative of error with respect to derivative of the hidden state at that same time step times derivative of the hidden state at time step k over derivative of the, or d hidden state time step k minus 1. And then you expand out all those like DHK minus 1 until you get to DI, right? And then, or D, sorry, this should be dh sub I and then dh sub I over dw. So basically when you expand all that out, you find out that like each of these dhk over dhk minus 1 is less than 1 if your weight values are small. So specifically, I think if the largest like eigenvalue of the weight vector is smaller than 1, then all of your DHT minus 1 is going to be less than 1. And that's also like supported by the tan function. So basically, if you go back to this slide, h sub k plus 1 equals tan h of weights h times hk. So if you differentiate this with respect to the weights, like weight sub h, so the hidden state weights, then you get something like weight sub h times tan h of whatever's inside. So if weight sub h is really small and tan is always between -1 and 1, then you can imagine that at every time step, the derivative has to the derivative of h has to be less than the absolute value of the derivative of h k plus 1 with respect to hk has to be less than 1. So if we go back to here, that means that each of these terms or each of these factors in that product is going to be less than 1. So when k is a lot greater than I, then this entire product goes to 0. So that basically means that it's like the error at time step k does not really depend on the hidden state at time step I when I is a lot less than k. And as a result, the RNN basically just won't learn how output k depends on a small I, or like an input at a small value of I. So the solution for this is LSTMs. But before I talk about LSTMs, I'm going to see if there's any questions about this. Yeah, so does anyone have any questions?
Wait, actually, real quick, can you explain the difference again between the RNN like many-to-many type 1 and type 2? Like, why is I don't really see the difference. So yeah, could you go over that again?
Okay. So that's also going to be a little more clear when I talk about seek to seek, but the basic idea is that many to many is where you kind of process an entire length of, or an entire sequence. And then after you process that sequence, you then produce a bunch of outputs later. So the outputs that you produce later might not be the same length as the initial input that you passed in. So one example of this is like language translation. So if you're translating, I don't know, like Chinese to English, then obviously the lengths of the sentences are not going to match, right? So you would kind of first have to process the entire Chinese sentence and then get some kind of context and then process and then like pass that back into the rest of the neural network and produce like a different length output. So that would be type 1. Type 2 is for every single input token that you feed in, you're producing one output token. So this would be like if you were taking that English sentence and then instead of like translating it to Chinese, you were just labeling each word in the English sentence as, I don't know, like pronoun, like pronoun, verb, adjective, whatever. So in this scenario, there's one output for each input. So the sequence lengths match. Does that make sense?
Yeah, cool. That makes a lot of sense. Thanks.
Okay. Any other questions? Yeah, this math is kind of complicated, but from what I've heard, at least, I think this is like a really popular interview question. So yeah, if you get this, you'll feel very big brain. All right. So if there's no more questions, we'll move on. So the solution to this kind of vanishing gradient problem is LSTM, and that stands for long short-term memory. And as a side note, there's also other kind of different models. One is the GRU, gated recurrent unit, and they all kind of share the same principle as the LSTM, except the GRU only produces a hidden state and no cell state. So I think this is used a lot in natural language processing. But like empirically, the difference between LSTMs and GRUs is kind of small. And like basically they perform pretty much identically. There's not like that big of an advantage of one over the other. So if you understand LSTMs, then you should be good to go for GRUs. So this is a picture of an LSTM cell. So there's a lot of stuff going on here. So I guess we'll unpack like what's happening in this cell. So basically, there's two kind of state vectors that are being passed from time step to time step. So first there's the hidden state like we had before. And then there's also the cell state. And the kind of very basic like intuitive idea behind the cell state is that it's storing long-term information. So if the hidden state can store like very recent information, then the cell state is in charge of remembering what happened in the distant past, plus all of the recent information too. So the reason this solves the vanishing gradient problem is that d c sub t over d c sub t minus 1 is now no longer like always less than 1 or greater than 1. So if we look at the previous slide, this dht minus 1, this is what's causing the problem, and this is what's causing like the gradient to shrink when you backpropagate it through time, right? And the problem with this is that since the weight matrix is kind of, you can think of it as like constants for each, like before you update it, it's basically constant for like every time step. So it doesn't vary from time step to time step, like we talked about parameter sharing. So that means that if the weight values are small, then at every single time step, this derivative is going to be less than 1 or it's going to be greater than 1. So you're basically always guaranteed that the gradient is going to vanish or it's going to explode. And that's bad. But here you have this like dct sub dct minus 1, which is sometimes greater than 1 and sometimes less than 1. So for some time steps it's greater, and for some time steps it's less. And as a result of that, when you multiply a bunch of them together, you're not guaranteed that it's going to vanish or it's going to explode. In fact, it's very unlikely that all of them are simultaneously less than 1. And even if it is, the network generally learns to correct for that on its own. So this provides a really nice solution to the vanishing gradient problem. So the way that the LSTM cell works is that it takes the input, the hidden state, and the cell state, and then it uses a sequence of transformations to process them, and it returns a new cell state and a new hidden state. And that new cell state and hidden state is passed to the next time step. And you can think of like the RNN cell or the LSTM cell as having different gates. So from left to right, you have what we call a forget gate, which is that first, like you see the sigmoid function, and then going into a multiply, a pointwise multiplication by the cell state. Oh yeah, I forgot to mention that in this diagram, the cell state is on top and then the hidden state is on the bottom. So yeah, that first like kind of vertical line is the forget gate. The middle stuff, everything that kind of points up to the plus, the pointwise addition, that stuff is all the input gate. And then everything else is the output gate. So it uses these gates to update the cell state and to produce a new hidden state. And then when you're obtaining your output, you're just going to transform the hidden state, just like you did for vanilla RNN, and you're kind of going to ignore the cell state. So after like you use that cell state, you throw it away and you don't care about it anymore. So I'll go over basically like how the transformations work very briefly. So generally you don't really have to know about this, but it's good to kind of have a concept of what the network is doing. So basically in the first step, it's taking the hidden state and concatenating it with the input, or you don't have to think about concatenating, but basically like you have that same like transformation as before, where you have hidden weights and input weights, and then you multiply the input by the input weights, the hidden by the hidden weights, and then you add those together, which is basically the same as concatenating them and multiplying them by a single weight matrix. So yeah, from now on, we're going to think about like concatenating the hidden state and the input and then multiplying by a single weight matrix. After you get that kind of like new like hidden state prime, we'll call it, you apply a sigmoid to that, and then you multiply that by the cell state. So the product of this is basically, you can think of the sigmoid as like a vector telling you the importance of each element of the cell state, and what you want to forget. So that's why it's called the forget gate. So if the value if the value of the like if the value after applying sigmoid of that vector is close to 0, then it's going to multiply, or it's going to shrink the corresponding value in the cell state. So it basically wants to kind of forget that information. And if it's close to 1, then it wants to remember that information. Oh, also a side note here, you have to enforce that the cell state and hidden state have the same length. Otherwise, this network is not going to work. And that's just because there's like pointwise operations that you have to match. Yeah, so the next one is the input gate. So after you kind of do the like forget gate operations, you then apply the same sigmoid function to that, or so you have another like neural network layer where you multiply the concatenated input and hidden state by a different set of weights, and then you multiply that result by or you sigmoid that result, and then you do another set of weights, multiplying it and then tan hing that result, and then you pointwise multiply the tan h result and the sigmoid result, and then you add that to the cell state. So the basic idea behind that input gate is that it kind of updates the cell state with your new information. So basically, the neural network with the tan h activation function, or sorry, the weights that have the tan h activation, those are what produces like basically a candidate update to the cell state. So that's like, it's like saying, oh, I think that we should update the cell state like this. And then you're multiplying that by the sigmoid. So the sigmoid tells you, like, it kind of modifies your candidate, and it tells you, okay, so these parts were good, these parts were bad. So I'm going to scale these parts by 1 and scale these parts by 0. And then we're going to multiply those together into the final like cell state update, and then add that to the cell state. So now you have your updated cell state, which gets passed on to the next layer. And that updated cell state is also used to produce the next hidden state. So in your output gate, you again apply another neural network layer with another set of weights and a sigmoid activation function to your concatenated input and hidden state. And then you combine that using a pointwise operation with your cell state, which you apply a tan h to. And that produces your next hidden state. And yeah, the hidden state is drawn on top because it can also be used to produce the output. So that was kind of a lot of information to unpack. So does anyone have any questions at this point? All right, moving on. Yeah, so now that we know kind of how the basic LSTM and RNN cells work, I'll talk about how you can stack them to make more complicated models. So, oh, actually, before that, I wanted to mention that it's important to note that all of these neural network layers have a different set of weights. So you're basically, for this case, you're training 4 sets of weights, and each set of weights is operating on the concatenated like input and output layer, or sorry, input and hidden state. Yeah, so stacked RNNs. So the plus side to this is that it can obviously model more complex patterns. So the only way to make like a single RNN cell more complex is to increase the size of the hidden state. But there's kind of a limit to that, and like increasing it past a certain point isn't going to do much for you. So the solution is to stack them. So just like we have like deep neural networks where there's a lot of different layers, there's also like deep RNNs where there's a lot of different cells. So you can see like a visual of that. Basically, if you stack them and then unfold them, it looks like this like lattice structure where like the going from left to right is going from like past to future in time steps, and then going from bottom to up is going from layer to layer. Yeah, so basically the first layer, or the bottommost layer, takes the original inputs, and then it produces this mapping. So like the bottom layer just takes the original input and the hidden state from the like previous time step of that layer, and produces the next hidden state for that layer. And then layer K, so like every other layer, takes the hidden state of layer K minus 1 at time step T. So after layer K minus 1 has produced its hidden state, it feeds that into the next time step of layer K minus 1, and it feeds it into the current time step of layer K. And then basically layer K uses that hidden state as input. And then it also uses its own hidden state as the hidden state. So it produces a new hidden state according to this function, or like according to the function that takes this input. And the important thing to note here is that because we want to model more complex behaviors, we don't share weights between layers. So parameter sharing does not apply from layer to layer. And also, if we're using LSTMs, we generally don't share a cell state between layers. So the cell state is not passed to the next layer, only the hidden state is passed to the next layer. And finally, the output is only going to be obtained from the final layer. So again, it's like a transformation of the hidden state of the final layer. And yeah, so you don't, in terms of output, you don't care about all the previous hidden states. So does anyone have any questions on how you stack RNNs? Okay, cool. So RNNs in practice, basically I'm going to talk about like how you use them in Torch and TensorFlow. Actually, I'm not going to talk about TensorFlow, I think, just Torch. So in PyTorch, the different types of RNNs are like how you construct them is pretty straightforward. It's just torch.nn.rnn or LSTM or GRU. And again, the RNN is pretty much not used anymore, so you shouldn't be using that too much. The parameters that you pass in are going to be your input size and your hidden state size, and then your number of layers. So this hidden state size and number of layers, those are hyperparameters that you can adjust to your liking. So like if you have a larger hidden state, then obviously it saves more information, but it can also like overfit or just like memorize data, which is not good. And it can also be a lot harder to train. But if your hidden state size is too small, then your RNN is not going to be remembering enough information and it won't perform well. So you have to kind of find the right hidden state size for your specific model. As inputs, so this is what like you pass into your model, and it like through the forward function, it produces the next hidden state. So you pass in your inputs, your initial hidden states, and your cell states. So basically, when you're passing the input, you can pass in an entire sequence, and then you just need the initial hidden state for each layer. And you can usually in PyTorch, you can just call some like init function to initialize those for you. And yeah, if you're doing an LSTM, you also have to make sure that you have initial cell states. And then after that, the model just handles like the entire sequence on its own. And yeah, usually you would default like the initial hidden cell states just to all zeros. And then for the outputs, it outputs it gives you the outputs at every time step, but only the final layer. And then for hidden state and cell state, it gives you those at the final time step, but at every layer. So if you like go back to that kind of lattice structure, as outputs, it kind of feeds you that like top edge and the rightmost edge, if you want to think about it like that. Yeah, so now we're going to talk about seek to seek, which is kind of the last little section of the workshop. And this is also going to be what the notebook covers. So seek to seek, or seek to seek, stands for sequence to sequence. And this is going to be your many-to-many, I think it was type 1 that I talked about before. So the idea behind this type of model is that you have this encoder-decoder structure. So you pass in your sequence of inputs. It goes through an encoder and it produces some kind of context, which is just like the final hidden state vector usually. And then you pass that context into your next, like your decoder model. And then that decoder recursively applies the LSTM cell on the outputs of like the previous time step. And it uses that to produce like an arbitrary length output. Yeah, so like I said, the encoder is just for producing the context, which is the final cell state and hidden state. Decoder takes that as the initial input and or initial like internal states, and then it recursively applies or it recursively like takes its output at time step I, passes the output in as input to time step I plus 1, and then it goes until the output is a stop token. So for example, in natural language processing, um, yeah, so this is an example in natural language processing. So if you were trying to answer a question, then your input might be the question. So like, how are you? It produces some context, and then it passes that context into the internal states of the decoder. So that's how the decoder is initialized. So the decoder takes as its first input some kind of default start token. So here, sorry, here there's like some go token that it passes in. So given that context and that start token, it produces what it thinks should be the first output. And then it takes that first output and feeds it in to the next time step as input. And then it uses that to produce the next output. And it keeps going. So here it's not depicted, but it keeps going until it basically produces an output that tells it to stop. So there's going to be a start token and a stop token. And the stop token is just like telling the LSTM, oh, we're done. And we don't want to like recursively feed in outputs anymore. So can anyone think of a kind of problem with this? If you're if during training, you're always feeding in the output at the previous time step, can anyone think of like why that might not work? Okay, so I guess I'll give you guys the answer. So basically, it doesn't work because it's very, very slow to train. So if you were thinking of like a neural network that's trying to output a sequence length of like 500, and in the beginning, like you have this neural network has no information on what it should be doing, then like when it's trying to produce like the first input, instead of I, it might produce some like random word like cat. And then at the next time step, it basically has to learn how to take that incorrect output, so like cat, and then turn it into the correct output, which is am, right? But that's like really hard to do, and we don't even want it to learn how to turn incorrect outputs into correct outputs. So basically, if we don't do this thing called teacher forcing, and we just like naively just feed in the previous output to the next time step, even during training, then while we're doing training, the decoder is first of all not going to learn, and even if it does learn, it's probably going to learn in the wrong direction, and it's going to take a lot longer to converge. So the way we fix that is this thing that we call teacher forcing. So basically during training, instead of recursively feeding in the outputs to the next time step, you feed in the actual output at time step t to the decoder at time step t plus 1. So this would be like your label. So if your input was how are you, and then your training label was I am good, then the input to the decoder would be go I am good, and then the output would be I am good stop. So yeah, so basically regardless of what this first, so like when you pass in go, maybe your decoder predicts cat, right? But regardless of that, it's still going to pass in I to the next cell, and then the decoder is trying to learn to map I to am instead of cat to am. and that helps the decoder converge a lot faster. So there is a downside to this, which is that like if you overuse teacher forcing initially, like in your training, then while you're testing it, it's going to have really erratic behavior, because when you're testing, it's no longer feeding in that like correct input. So basically, you're kind of spoiling your decoder to make its job a lot easier. And then in your like testing phase, it might not be able to perform the way you expect it to. So for example, if you were trying to produce like a 500 length output, and then you always use teacher forcing in your training, then like if during your test phase, like one of those 500 outputs is wrong, then in the future, it's going to be recursively passing in those wrong values, and it's going to get worse and worse and worse. But if you like mix in a little bit of like non-teacher forcing, like recursively defined training into your teacher forcing training, then it's generally going to generalize a lot better, and that like teacher forcing bit is going to help it converge faster. So usually we do like some ratio of teacher forcing versus not teacher forcing during our training. So a small side note, if you're interested in natural language processing, then I would suggest you to take a look at the attention model, which is an improvement over like the standard sequence to sequence approach, or like the traditional, or I guess the old sequence to sequence approach, for processing for natural language processing. So the basic idea, I'll just explain it really briefly. The basic idea behind the attention model is that the encoder produces some context, but then the decoder doesn't only use that context. It also kind of has this like separate part of the decoder that takes each output or each like hidden state in the encoder like sequence of outputs. So like for the how are you example, there would be 4 hidden states associated with 4 different time steps. And then the decoder takes those and tries to associate each time step with some kind of combination of those. So maybe it thinks that for the first time step, the hidden state associated with how is really important, and the hidden state associated with R is a little bit less important, and the hidden state associated with U and question mark are not very important. So then it takes as input kind of, it also takes like a weighted sum of those hidden states of the decoder. And then it uses like that weighted sum to help it make its prediction. So basically that adds like a lot of context information on like which decoder output depends on which encoder output. So that was kind of a complex explanation. If you're curious, you can check out like the Medium articles on this. They're pretty comprehensive. And generally people like when doing natural language processing, people basically just use like the attention model or like transformers. And they don't really use this like naive implementation of sequence to sequence anymore. But this is what we are going to be doing in the notebook, to just get a feel for how, RNNs generally work. So that is the end of the workshop. So do you guys have any final questions about anything we've covered? All right. If
Real
not,
quick, one question about
yeah.
the start and stop tokens is like, is that like just another character? Like you just pick a character, or is that like something special? So yeah.
Yeah, so you basically just think of it as another character. So for example, if your inputs were all like word embeddings, then like, so I guess, okay, so in practice, maybe the workflow or the pipeline would look like you take your raw word, pass it into BERT or something to get a word embedding, and then pass that into your model. So if your word embedding is like all your words, then you have to pick a start token that's not equal to any of your word embeddings, and also a stop token that's not equal to any of your word embeddings. So you basically add 2 words to your dictionary, and then those are kind of just the dummy words that signal when you start and stop. But yeah, if you can think of it as like a different like type of input in your input dictionary.
Okay, yeah. And then BERT produces like an embedding, right? It's like not another word.
Yeah.
It's like a
Yeah.
vector. Okay, cool.
Yeah. So if you guys want to read the BERT paper, it's actually really cool how it works. Highly recommend it. It's a fun read. Any other questions? All right. So Alexi, do you think we should stay for like working on workshops or notebook, or do we just
Yeah,
end
we
it?
could do that. I don't know. There's only 3 people or 4 people.
Yeah.
Yeah. Oh, there's only 3 people. Do you guys want to stay, or would you rather like do this on your own time?